All right, welcome to the last lecture in chapter 4. For those of you that are math lovers, you're going to like the last part of this chapter 4. You're going to like the ending here. So what we're going to do with this last little section is we are going to bring back this idea of molar mass. We're going to bring back this idea of Avogadro's number, and we're going to add a couple wrinkles now that we're looking at compounds. So we're going to do the same sort of math, but with a compound instead of individual atoms. So the first thing I want to talk about is something called the molecular mass. So the molecular mass is the mass of an individual molecule, and it's the molecular mass or molecular weight of the entire compound. So before we looked at molar mass, so that was just of each individual atom. So what is a carbon's molar mass? What's a sodium's molar mass? Well, now that we've built these compounds, we can talk about how that changes the molecular mass. What's that mass of the whole molecule? Okay. So it's the mass of 1 mole of that compound. This is the formula that your textbook gives, and I think that it's way more challenging than it should be, but I'll put it up here because it's from your textbook. But essentially what they're saying is when you have a formula, so let's use N2O5, okay? So what they're saying is when you have a formula, you're going to take the number of atoms in the first element, so that would be 2 in this case, times the atomic mass of the first element. So you would go to your periodic table, you would look up your the atomic mass of nitrogen, and you would multiply that by 2. So if you don't already have a periodic table in front of you, now would be a really good time to get one. So the atomic mass of nitrogen is roughly 14, so I would take 14 times 2. Then you're going to add that to the next atom. So I'm going to take the number of atoms of the second element. In this case, there's 5. And I'm going to multiply that by the atomic mass of oxygen. So again, go to your periodic table. Oxygen is essentially 16. Excuse me, so 5 times 16. So add those two numbers together. That's the molecular mass of this molecule. And there's a ... just in case there's more than 2 atoms. Okay, it's pretty simple. So let's work through an example together. So we're going to determine what is, I don't know what's going on. All right, we're going to determine what is the molecular mass of water. So water is H2O, okay? So here's how I kind of organize the problems. Here's how I organize my thoughts. So hydrogen is the first element. I'm going to look up the molar mass for an individual hydrogen. So that's going to be 1.008. And then I'm going to multiply that by 2 because there's 2 of them. Okay. And then I'm going to determine the molecular mass for oxygen. So 15.999, according to the table I have in front of me. And I'm going to multiply that by 1 because remember there's an implied 1 here. We have 1 of them. And then I'm going to simply add those two numbers together. So let me go ahead and do that. So 1.008 times 2 gives me 2.016. 15.999 times 1 gives me 15.999. And I add those together, and I get 18.015. And then again, the units for this are grams per mole. Or another way to say this is 1 mole of water equals 18.015 grams. Okay. So that's molecular mass of the compounds. So we can take this idea of molecular mass in combination with Avogadro's number to determine number of molecules. So I can go to a scale, I could weigh out a certain number of grams of water, and I could determine exactly how many molecules of water that is. Okay. Here I've been using water, but here they use carbon dioxide. So I could weigh out a certain number of grams of carbon dioxide, use molecular mass to get to moles. Then I could use Avogadro's number to get to molecules. And this portion of the exercise, let me get my pointer so you can see where I'm at. This portion of the exercise should be review from chapter 1. I'm going to run through examples just in case it's a little fuzzy, but this is just review, and this is really the only new step. So here's an example we're going to work through together nice and slow. So an aspirin tablet contains 325 milligrams of acetyl salicylic acid. There's the compound for acetyl salicylic acid. I want to know how many molecules of acetyl salicylic acid does it contain? Okay. First little wrinkle here, like most medications, this one is dosed in milligrams, but all of our calculations are always kind of based on or start with grams. So that's going to be the first step, is going from milligrams to grams. Then we can take off through this path. Okay. So let's just do that unit conversion quickly. So we've got 325 milligrams of C9H8O4. Again, I teach the train track method. So milligrams is going to go diagonal, grams on top, so that milligrams is going to cancel. And in 1 gram, there's 1,000 milligrams. So we've got 0.325 grams of this guy. Okay, so just a quick unit conversion here. So I'm just gonna, just to save space, I'm just gonna cross that out and put 0.325 grams. That way I can remain on this slide with you. All right. So kind of our path that we're gonna take is grams to moles to molecules. So that's our map. And to get there, we're going to use molecular mass and then Avogadro's number. Okay. So the very first thing I do for every unit conversion problem that ever existed is I write down the measurement that was taken. So the 0.325 grams. And it's important that you guys put of what? All right, so the first step is grams to moles. So what unit am I trying to get rid of? This goes on the bottom. And what unit am I interested in? Moles, that goes on the top. All right, so for another chapter or two, well, no, we're going to change it in this chapter. For right now, when you're going between grams and moles, the number 1 will always go with moles. Now, where do I get this number for grams? Yeah, I got to go to the periodic table. I got to figure out the molecular mass for this guy. So carbon, molecular mass for carbon, peek at your periodic table, 12.011. And I'm going to multiply that by 9 because there's 9 of them. Hydrogen, peek at your periodic table. The molecular mass for hydrogen is 1.008. And I'm going to multiply that by 8 because there's 8 of them. And then oxygen, there's 15.999 is the molar mass. I'm going to multiply that by 4 because there's 4 of them. And then once I get here, I'm going to add those numbers together. Okay. So give me just a minute to plug this into my calculator. So 12.011 times 9 equals 108.099. 1.008 times 8 equals 8.064, and 15.999 times 4 equals 63.996. And then I add these together to get the molecular mass. So 108.099 plus 8.064 plus 63.996. And I just hit times. 108.099 plus 8.064 plus 63.996 equals, oh, that's much better. 180.159 grams in 1 mole. So that's the number that's going to go down here. Okay. This is the only new step. Everything from here is review. Okay. Multiply across the top, divide by the bottom. So 0.325 times 1 divided by 180.159 equals 0.00180 moles. Oops. Of C9H8O4. Okay. That's step 1. Is it asking about moles? No. It is asking about molecules. We have one more step here. All right. So next step is going from moles to molecules. So the very first thing I'm going to do is start a new problem. And I'm going to start with this number right here. So 0.00180 moles. My unit moles is going to go on the bottom because that's what I'm trying to get rid of. Molecules is going to go on the top. And there's really no way to shorthand that because if I shorthand it, it's going to look like mole. All right, so the number 1 is still going to go with mole for now. And what number goes with molecules? Yep, Avogadros. Okay. Multiply across the top, divide by the bottom. So 0.00180 times 6.022 times 10 to the 23rd. And I get 1.08 times 10 to the 21st molecules of acetyl salicylic acid. And if I teach you nothing else in this class, I want to teach you, does this make sense? Okay. Does it make sense that a tablet of aspirin would contain a ridiculously large number of molecules? Yeah, it does, right? Molecules are teeny, 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 tiny, so we would expect that number to be pretty large. Okay. So that's the first one, introduction of this idea of molecular mass. The next thing we're going to introduce is a relationship or an equality that is built into the chemical formula. So the chemical formula indicates relative quantities of each of these compounds. So here we see a compound. This compound is carbon, 2 chlorines, and 2 fluorines. When we do these comparisons, we usually do them in the unit of moles. But when I introduce this idea, I like to think about molecules and atoms because that's a little bit easier for us to wrap our brains around. So looking at this molecule right here, I could draw a picture of it. I don't really know how it's all attached together, but we'll say chlorine, chlorine, fluorine, fluorine, right? 2 chlorines, 2 fluorines, okay? For every one of these molecules, so one molecule of this guy, how many individual atoms of chlorine do you see? Well, let's count them. 1, 2. So I see 2 atoms of chlorine. We could do the same thing for carbon. So for every one molecule of this, how many carbons do you see? Just 1. And for every one molecule of this, how many fluorines do you see? 2. Okay. So here we have this new equality that links the number of molecules to the number of individual atoms. But in chemistry, when we try to compare one thing to another, we like to compare apples to apples. So we'll always do this in the unit of moles. Okay, so think of it as a little detour when you're in Mole Town. Okay, so let's look at this example. We're already in Mole Town, so I kind of did the hard work for you. We're in Mole Town. So I want to know how many chlorine atoms are in 38.5 moles of this compound. So to do this, we're going to have to go from moles of the compound to moles of individual chlorine. And then we've got one more step, right? Then moles of individual chlorine to atoms of chlorine. Okay. So again, this is the only new step right here, breaking it down. This is, again, little review. Okay, so let's go ahead and do this. So what's the first thing we write down for every unit conversion problem that ever existed? We write down the information or measurement that was taken. So 38.5 moles of our compound. And here you see it's incredibly important to put of what. Okay. So what goes diagonal? What goes on the bottom? Well, it's going to be moles of the compound, whatever it is we're trying to eliminate or get rid of. What's our destination in this first step? What's the first unit that we're going to put on top? Yeah, we're going to put moles of chlorine on top. That's our destination. Okay. So mole on top, mole on bottom. The number 1 is always going to go with the compound. So another way of thinking about this is for every 1 mole of this compound, how many moles of chlorine? Yeah, 2. 2 moles of chlorine. Multiply across the top, divide by the bottom. 38.5 times 2 divided by 1 gives us 77 moles of chlorine. That's the new step. Okay. Is it asking for moles of chlorine? Well, of course not. It's asking for atoms. So we've got one more step that we need to do here. Okay. We need to go from moles of chlorine to atoms of chlorine. So I'm going to erase this. And I'm going to use my answer from that first step to start a new train track. So 77 moles. So we've got 77 moles of chlorine. Moles of chlorine go on the bottom. Atoms on the top. I don't know why my pen's breaking up. It says atoms. Okay. So again, 1 mole goes with mole. And what number goes with atoms? Avogadro's number. So multiply across the top, divide by the bottom. So 77 times 6.022 times 10 to the 23rd. And we get 4.64 times 10 to the 25th atoms of chlorine. Okay. So again, new step is breaking down the compound to individual element. And we do that in the mole, the unit, the mole. And then that last step was review. So why don't you guys go ahead and see if you can knock out this problem. Go ahead and pause the video, work it out, and then I'll quickly work it out with you. All right. So first thing I'm going to do is just kind of map out my thought process here. So calculate the number of carbon atoms in 25 grams of this isopropyl alcohol. So I'm in grams of isopropyl. I need to go to moles. So anytime you're in grams, your first instinct should probably be to go to moles. Then it's not asking about the molecules of that whole thing. It's just asking about carbon. So then I'm going to go to moles of carbon. And then lastly, atoms. Okay. All right, let's dive in. So we start every unit conversion that ever existed, ever, with the measurement that was taken, so the 25 grams of isopropyl. First, we go to moles, so grams on the bottom. Moles on top. And in 1 mole, we've got to determine number of grams. So I'm going to do that quickly over here to the side. So, carbon is 12.011, and there's 3 of them. Hydrogen is 1.008. There's 8 of them. And oxygen is 15.999. And there's 1 of them. And then once I get all that, I'm going to add it together. Okay. So 12.011 times 3 plus 1.008 times 8 plus 15.999. So I get 60.096. So that's the number that goes down here. All right, multiply across the top, divide by the bottom. So 25 times 1 divided by 60.096, and I get 0.416 moles of isopropyl alcohol. Okay, so that was step 1. Step 2, new step, going from moles of the compound to moles of individual atoms. So I'm going to come down here. I'm going to do a different color just so it sets apart a little bit. I take the answer from the first step and I start a new problem. Okay. So moles of isopropyl go on the bottom because that's what I'm trying to get rid of. Moles, what's our destination in the second step? Moles of individual carbon. The number 1 will always go with our molecule. How many carbons do we have in one molecule of this? Yep, we got 3. So that goes up there. Multiply across the top, divide by the bottom. So 4.16 times 3 divided by 1 gives me 1.248, and that is moles of carbon. Now we got to take this final step from moles of individual carbon to atoms of carbon. So 1.248 moles of carbon. Train track it. Moles of carbon go on the bottom. Atoms of carbon go on the top. The number 1 goes with mole, and Avogadro's number goes up here. All right, so multiply across the top, divide by the bottom. So 1.248 times 6.022 times 10 to the 23rd, and we get 7.52 times 10 to the 23rd atoms of carbon. So that ties together a lot of math skills, some of them new, some of them review. And the only way to get good at these math problems is to practice, practice, practice. That wraps up chapter 4. So that's it for chapter 4. We will dive into chapter 5 very, very soon. Hope you guys found this helpful.